So we have solved mini story number 1 going from 1 to 2. We have solved mini story number 2 and going from 2 to 3. And so finally we're going to solve mini story number 3, which is going 3 to 4. So we've got two blocks. They have mass m plus m put together. They're moving with speed u, and as they move, they're going to compress this spring. Okay, so they're going to compress this spring. So let's go ahead and draw the forces that are acting on these blocks. So there's going to be, there's going to be the weight of the blocks, and because the blocks are stuck, I'm just going to think of them as a single block, right? There's the normal force, and there's still friction with that surface, so there's still going to be a frictional force over here. And of course, there's going to be a spring force over here, right, F sub s. So this is what the force diagram for this object is looking at. And what's happening is that the block is slowing down as it compresses the spring. And so what we're doing is we're trading speed for spring compression, right? So we're taking energy that is in the form of the kinetic energy of this block, and we're pouring it into the potential energy cup for the spring. So this is going to be a conservation of energy problem. So let's go ahead and set up my conservation of energy equation. So 3 to 4. We know that the final energy is equal to the initial energy plus the work due to other forces. So at the very end of the problem, the blocks are just sitting there doing nothing. So there is zero kinetic energy, but there is potential energy because the spring has been compressed at distance d. So the spring has some potential energy 1/2 k d squared. At the beginning, the spring is not stretched or compressed, so there's no potential energy there, but there is kinetic energy on the blocks. So I do have this potential energy. And finally, there is work done by other forces. So gravity does no work because it's perpendicular to the displacement. The normal force does no work because it's perpendicular to the displacement, but friction is going to drink some energy. The friction is pointing to the right and the displacement is to the left. So friction is doing some negative work. It removes energy from the system. So minus F times the distance moved is d in this case, according to my picture. So there you go. This is my conservation of energy equation, just as before. The normal force is equal to mu times the normal, which in this case is going to be mu times the total weight of the two blocks. So let's go ahead and plug that in. I have 1/2 kd squared is equal to 1/2 m plus m u squared minus mu m plus m g times the distance d. And so what we want to do is we want to find out how much the spring is compressed. So what I'm going to do is I'm going to go ahead and I'm going to, let's see, I'm going to multiply by 2 first. So let's just do that. Kd squared is equal to m plus m u squared minus 2 mu m plus m g over d. Now I have k here and I have m plus m over there. So what I'm going to do is I am going to go ahead and first divide by m plus m, and you'll see why. So I'm going to have k over m plus m here times d squared is equal to u squared minus 2 mu g times d. But remember, if you have a mass on a spring, then what you have is a simple harmonic oscillator, and the angular frequency of that simple harmonic oscillator is given by omega squared is equal to k over mass. And in this case, the mass is big M plus m. So this prefactor here is just omega squared. So I can take this equation and just write it in a little bit of a nicer way, in this way. let me go ahead and move the 2 mu GD. I'm going to take this term and move it here. I'm going to take this term and move it here. So I'm going to have omega squared d squared plus 2 mu GD minus u squared is equal to 0. And what's this? This is a quadratic equation for D, right? So this is a quadratic equation for D where this is playing the role of A. This over here, sorry, just this part is playing the role of B, and then minus U is playing the role of C. And so we can go ahead and plug into our quadratic equation, sorry, not D squared but D is equal to minus B plus or minus the square root of B squared minus 4AC divided by 2A. So we can go ahead and plug all of these values into our expression for D, and that's going to give us our final answer. So I'm not going to do the algebra because I don't think it's worth doing. In fact, I just defined A, I just defined B, I just defined C. So this is actually a complete solution because you know what A is, you know what B is, you know what C is. So if I gave you numbers for K and M and all these things, you would actually be able to plug this into a calculator and get D. So this is our final solution. This is how far the spring is compressed.